so everyone is on mute. If you have any questions throughout the webinar or at the end, please feel free to use that questions box in that GoToWebinar application, and we can answer them either throughout the presentation at the end, or we can also email you afterwards with the answers to those questions. Okay, and also, because we are recording the webinar, everyone is going to receive an email following. And that email will have a survey on it, and it'll also have a link to this recording. So you can feel free to view it as many times as you wish. All right, so let's get started. Today's presenter is Heather Versillo. Heather is a certified lubrication specialist and is a data analyst for Test Oil. She has played a significant role in Test Oil's technical operations department, and she developed the material identification analysis as well as the deposit classification tests. And those are used to determine the root cause of machine and lubricant failure. Heather has been a guest presenter at several industry events hosted by entities such as NORIA and STLE, where she discussed these specialized test methods and root cause analysis procedures. She's also hosted several webinars and training sessions with the goal of helping customers better understand their lubrication systems. So Heather, if you're all set, why don't you get started?
All right, thank you very much for the introduction, Ashley. And thank you everyone for joining me today to learn a bit about lubricant compatibility studies. As Ashley mentioned, I'm currently with the data analyst department at Test Oil, meaning that I am looking at the reports that are generated from routine analyses, as well as kind of one-off testing. When I was in the technical operations department, I was lucky enough to be involved in some R&D type work. So I really got to kind of dig into the different testing and dig into failure modes and root cause analyses with that. Lubricant compatibility studies is a pretty interesting field in that there are mixtures that occur in the world and for various reasons, and we'll be going over that a bit today. On the agenda in general is that we're going to learn a bit of history as to how modern lubricants came to be first. Then we'll identify why compatibility testing is important and discuss the testing process, and then we'll determine what do we do with these results now that we have them. So oil is oil, right? And we can just mix two products of the same viscosity and we'll be fine. Many of you know that this is kind of thinking is a bit off base in today's vast world of lubrication, but I like to dig in a little as to why this kind of thinking is no longer prevalent or should not be prevalent. Many of us know that this kind of thinking does still come into play today, so hopefully these couple of slides here will give a brief history lesson with a basic timeline of how lubricating oil has developed. I always find it interesting to see where we've come from and where we're headed. And as you may suspect, archaeologists have found evidence of lubrication dating back to ancient Egypt. In the 17th century BC, we knew that large objects and stones were pulled across the ground or wooden planks to construct the great sphinxes and pyramids, and actually olive oil was used at that point in time. Following then in the 8th century, Greece was actually holding the first Olympic Games, and one of the most exciting events was the chariot race in which the axles were lubricated by animal fat, which is also known as tallow. And then in the 16th century, during this time, Leonardo da Vinci studied various topics related to tribology that included friction, bearing materials, and wear modes, just to name a few. His studies were recorded in manuscripts that were actually lost or hidden, not quite sure yet, for 150 years. But since these manuscripts were found, Da Vinci's often known, apart from being an artist, but as the father of modern tribology as a result of his contributions to the tribology field. And then we move on to the 1850s when the first oil well was drilled, and we were able to extract about 3,000 liters of oil per day. And this is really when the history of modern lubricating oils starts. During this time, it was also found that mixing crude oil with sperm oil would extend the life of the machine, and this is when lubricants were starting to become replaced by crude oil-based products rather than animal fats. And then in the 1920s, we have our first solvent refining method that was invented. And while the first synthetic hydrocarbon lubricant, or what we may know of as a polyalpha olefin, was developed in 1877. Synthetics were really commercially developed in the 20s. So then moving on to the 30s, this is when additives started becoming introduced to the world to enhance the performance of lubricants across multiple industries. And a couple decades later, synthetics were really being widely used in the aviation and aerospace industries due to the introduction of the jetliner. And obviously these jetliners required that lubricants perform at very low temperatures. And this is also about the time when multi-grade oils started becoming introduced to the market. And then we move on to the 70s, where we saw hydroprocessing technologies like two-stage hydrocracking. And this invention rapidly improved base oil performance and purification. And then in the 90s, only a couple decades ago, we started seeing modern dewaxing technology, or hydroisomerization. And this became widely used, which allowed for production of high-quality mineral oil lubricants that could compete with the fully synthetic oils. So now in the 2000s, we have many environmental factors that need to be taken into account when selecting our lubricants, as I'm sure as many of you know and have to adhere to some of these EPA-type regulations. And in addition, people within the industry continue to research to improve lube performance and meet various industry needs. So hopefully this gave you a basic idea of where we've come from and how we ended up where we are today. In the early 1900s, the thought, if we're out of the gear oil, just add some of the engine oil, may have been applicable. But in today's world, when there are about 10,000 different lubricants, and even more when you realize people mix them together, this thinking really can no longer be prevalent. The concept could even be dangerous today, resulting in shortened lubricant life or shortened machine life. And this is really a lot of the reason that I'm here today with you, is to provide information on a way to determine compatibility between lubricating oils. So today's lubricants are manufactured with high degrees of specialization, as we've kind of seen moving through the historical line there. Almost every lubricant used today started off as just a base oil. The American Petroleum Institute categorized base oils into 5 categories. Groups 1 through 3 consist of mineral oils that have been refined using different methods, and group 3s actually undergo a process that results in a purer base oil and are sometimes described as synthesized hydrocarbons. Sometimes you'll see those as actually listed as group 3+. Group 2 and 3 tend to be more resistant to oxidation than group 1 base oils. And these different chemistries are why we have the differences in the groups. Then we move on to our synthetic groups. And these group 4 consist of synthetic hydrocarbons called polyalpha olefins, or PAOs. And these have molecules that are very similar to groups 1 through 3, but they have much broader temperature range and similarity among the molecules dispersed in the oil. And therefore, they are really great for extreme weather conditions, such as in jetliners. Then we go to group 5 base oils, and these are a bit of a different animal since the category encompasses everything from phosphate esters to silicone to PAO-based oils that are also mixed with esters. And while lubricants within a certain group do share certain base oil characteristics, it doesn't mean that, say, 2 group 3 lubricants are compatible just because they have the same base stock. So the lubricants in our world today use base stocks that are formulated with specialized additives that have to be carefully selected so that we can impart certain performance characteristics that we desire for a specific machine or application. We have to carefully select them so that the additives are, first of all, soluble in the base oil, and secondly, that they function the way we want them to. And lubricant manufacturers spend many years developing a lubricant. Additives are typically used by application. So for example, we have gear oils that use EP or extreme pressure additives. These typically contain phosphorus, while turbine oils are often formulated with amine and or phenolic antioxidants. And each type of additive is blended with a base oil to enhance that base stock's properties in accordance with the intended application. So lubricant manufacturers will spend time developing and tweaking specific lubricants even after they've been on the market. And since lubricants are carefully crafted to give the required performance characteristics for a machine type, it's really imperative that the compatibility of different is tested if a mixture is to be used in a machine. So there's going to be times that products are mixed, and there can be numerous outcomes depending on whether or not the lubes are compatible with one another. If the two products are very similar with additives that remain relatively stable in solution, you may not see any negative consequences from the mixture. But there's also the possibility that while a mixture may visually appear okay, and at first no negative effects are noticed or apparent, there might be an impairment or a decrease in the lubricant's performance. For example, there might be a slight decrease in the ability of the fluid to separate out air or to separate out water due to incompatibility among additives of the mixture. The speed at which the incompatibility problems potentially develop over time, it can be provoked by several factors, and it can include, but it's not limited to, the nature of the incompatibility, which may include incompatible base stocks or additives, or the presence of contaminants already in the system. So what happens when we start mixing these special products and major incompatibility occurs? And what are the consequences or symptoms of that incompatibility? So first of all, we can have phase separation, which you can see in the test tube on the left. We actually have 2 layers there. Phase separation is identified when we have 2 or more distinct layers of the fluid present, and it can occur due to incompatible base stocks, such as mixing a potentially phosphate ester with a mineral oil, or mixing a polyalkylene glycol or PAG with a PAO fluid. When mixing oils, it's really important to consider that incompatibility is not just limited to the lubricants. The user should really be concerned with the 2 fluids compatibility, even with the system seals and hoses and gaskets and other machine components, in order to prevent degradation or damage to the system components. And then we have the 2-phase fluid, which can really just impair the system from receiving appropriate lubrication and load-bearing properties at that point. So then moving on to our second point, additive solubility issues can also arise for a variety of reasons. The additives might not be soluble in a certain base stock, or the additives from the 2 lubricants may react with one another and precipitate out of solution, resulting in additive flock. And you can actually see kind of the picture on the right shows some flocculate. You can see kind of a swirl in the middle of that, of incompatible additives in that mixture. So, and when these additives end up dropping out of the fluid, there's actually an increased risk of the gel, sludge, sediment, or varnish formation, and even the potential for filter clogging issues. So despite the potential visual major incompatibilities that can occur, the performance and physical properties of lubricants may decrease also, such as the ability to separate out water, air. We can have accelerated oxidation issues or even decreased rust and copper protection. So really what we're hearing here is that mixing different products for the most part needs to be done very cautiously, but what are the reasons that different products have to be mixed? And we primarily see 2 reasons. The first really is unintentional mixing, and the second is intentional mixing. So when we have inadvertent or unintentional mixing, it can really occur for a number of reasons. The most common reasons are really that there are mislabeled lubricants within the plant. There can be contaminated new oil potentially, or even it can be related to insufficiently trained personnel or topping off with a different product that maybe has a similar naming scheme to what typically goes in the system. So then when we go to intentional mixing, this can also occur for a number of reasons. It might be related to the company's purchasing practices, such as buying from the lowest bidder. It could be a change in lube suppliers, and this can necessitate switching to another product in order to consolidate. When receiving new equipment, it might be filled with an unknown lubricant. And then there's lubricant consolidation programs that become implemented potentially for purchasing practices or switching suppliers, or many of these reasons can be encompassed together. Or when doing a change out, it might just be impossible to remove all the old lubricant from the system when doing the change out. So given the issues that can occur, it's obviously safest not to mix the lubricants, but in the real world we know that mixing happens for one reason or another, and we really just need to know how to handle that. So if we have unintentional mixing, there are steps that can be taken to aid the determination of possible issues as well as the severity and implications of those issues from the mixture. The lubricant can, first of all, be tested to determine if the critical performance characteristics have been compromised. For instance, if say there was a new delivery of oil for a steam turbine and it was contaminated with a small amount of engine oil and it wasn't discovered until the oil had been added to the system, I would suggest testing the in-service oil that's actually in use in the machine for the critical characteristics as applicable to a steam turbine. So specifically, the ability to separate from water would be one, and rust prevention. If the lubricant meets the expectations, then an oil change might not be vital. However, the oil change might be warranted if the lubricant doesn't really function as it was intended or requires. In addition, you want to take steps to identify the root cause then of the unintentional mixing to prevent it from occurring in the future. Lube storage processes as well as personnel training should be really taken into consideration as potential opportunities for improvement. And after all, we are in the business of continuous improvement, so isn't that really the goal? So now if we do have products, on the other hand, that have to be mixed for any certain reason, we can do lubricant compatibility testing ahead of time to try to help assess if these two lubricants will work together. And two established methods that provide guidelines for determining lubricant compatibility are ASTM D7155 and Federal Standard 791C. And those are listed on the slide for reference in the future for anyone that might need them, and broken down a little bit more into their specifics. So in general, the methods that we typically involve with making one or more mixtures of the in-service lubricant and the candidate lubricant includes heating and then cooling the mixtures, and then observing the mixtures for any sort of signs of incompatibility, such as cloudiness or the presence of sediments. One of the first decisions, though, that has to be made in order to make this decision is what mixture ratios should be tested. At the very minimum, we always like to use a mixture of 50-50, but depending on the situation, additional mixtures might be included. For example, if the intention is to do a complete oil change, but say you know that there's going to be some residual fluid that's going to remain in the system and mix with the new fill, it might be worthwhile then to test a mixture that's 90% of the new oil and 10% of the oil currently in use. And then another situation might be that you are intending to gradually add the new oil to the in-service oil by topping off the system. You know, when it comes to that type of goal, mixtures of 25% new oil to 75% used oil and vice versa would be really worth considering. Even a combination of 90-10 and 10-90 mixtures would be appropriate when deciding whether to top off or not gradually with a different fluid. So we have a quick question here for you all to get you thinking a little bit, and I'll give you a few seconds to think about the answer, and then I'll get back with you. So we have virgin lubricants. Will they always be used when making the mixtures? True or false? And our answer for this one is B, false. There are going to be times where it is actually appropriate, even a necessity, to use an in-service fluid during the compatibility study, as we're going to find out right about now. So when it comes to our specific needs and details of the situation, it can also help to decide whether mixtures of only the virgin sample of the product in use or virgin samples of just the candidate products, or if mixtures of the in-service fluid should be mixed with the virgin candidate fluids. For example, if we have a turbine that we absolutely have to begin using another product with because, say, we're in an outage, this is the only time we can get to it for whatever reason, it might be beneficial to test the actual fluid that's currently in the system with the candidate new oil. Using a mixture like this will take into account any contaminants that are already present in the fluid, and that can actually cause an effect on the compatibility of the fluids. And another example, say we have a fleet of 50 gearboxes, and we are looking to use a new fluid, and the cost of testing all the in-use fluids would probably be pretty cost prohibitive. So in this type of case, we might want to test mixtures of the virgin sample of the in-use lubricant and a virgin sample of the candidate lubricant. And this would at least provide us a general idea of the compatibility between the two and what we can expect. So now that we've discussed a little bit about which mixture ratios would be appropriate, we can get back to the actual test method itself to help determine if the mixtures are compatible and acceptable for use. So as we kind of heard earlier, the mixtures are first heated and then cooled. After the heating and cooling process, the mixtures are then visually observed for multiple characteristics. And this is all known as Tier 1 of the testing process. We first evaluate the mixtures for clarity and also any development of sediment or flocculate. Cloudiness or sediment can indicate an incompatibility between the base stocks or the additive. Some customers choose to end the testing at this point and are satisfied if the mixtures are bright and don't show any signs of sediment formation. On the other hand, a second tier of testing may be desired to actually determine the physical properties of the mixture. So the second tier of testing, we're looking at the critical performance characteristics of the lubricant mixtures. Possible additional tests include anything from viscosity, acid number, base number, to something a little more expensive such as copper corrosion, oxidation stability, or pentane insolubles even. The second tier test really should be selected based on the lubricant type and the application that we're looking to use the mixture in. For instance, if we have an engine oil, we might want to select something like viscosity, base number, and pentane insolubles. On the other hand, for a combustion turbine, we want to select viscosity, acid number, foam, air release, rust, and oxidation stability. And then we can move along to a steam turbine. It sounds pretty similar to a combustion turbine, but we would definitely want to add demulsibility because that's a pretty critical characteristic and performance aspect that is needed for steam turbines. So once we have Tier 1 and Tier 2 compatibility testing completed, what do we want to do with the results now? So if we have the results, then they don't show any signs of incompatibility, saying they are compatible, we can proceed with caution. You know, you always want to keep in mind that the testing was completed under laboratory conditions and might not always produce the same results as real-life conditions in the field. And is that with any lube sample, routine testing really should be performed to monitor the fluid once it's actually in the system. And then what if we have testing that shows a minor incompatibility? If the results show minor incompatibility, you might just need to evaluate the potential impact, such as do the mixture show decreased ability to resist oxidation? And will this result in shortened lubricant life and therefore increase the cost over time due to more frequent oil changes? Or is it a certain performance characteristic that we can get past and deal with? And if it's not something you can get past, then you might want to look into doing a different replacement lubricant. So then finally, if we have a compatibility test that shows signs of major incompatibility, which might include something like significant amounts of sediment or really severely decreased performance characteristics, we can go back to actually one of our examples. If the intention was to mix the lubricants by gradually topping off the system, change of plans is definitely in order. If choosing one or more compatible replacement lubricants is not an option, though, then the changeout should be done using a complete oil change with a system flush to remove any residual lubricant. And you should definitely try to find a new plan of action if you do see major incompatibility as a result of the testing. So here we'll do a quick recap. And let's remember, it took thousands of years to achieve the specialized lubricants that we know today, and they're still developing new lubricants and increasing performance characteristics. And these, specialized additives based on the application in different base oils necessitates that we really understand that oil is no longer just oil. Mixing products can occur purposely and accidentally for various reasons. And as stated, it's better not to mix, but there are sometimes we just have to. And nowadays we are lucky enough that we do have ways to figure out if mixing will be okay. The use of virgin and or in-service lubricants and their ratios are really dependent upon the application and your goals. So we can use Tier 1 testing for visual inspection of any obvious incompatibilities, and then we can use Tier 2 testing to actually assess performance characteristics. And from that testing, we can look at the results to determine if the mixture is okay or has a minor or major incompatibility, and then you can determine your next course of action. So with that being said, that concludes my presentation, and if there's any questions, please feel free to ask.
All right, Heather, I do see that there are a couple questions, so if you have time to answer those.
Okay.
Okay. The first question is it necessary to test different batches from one supplier for compatibility checks? And that would be new oil from the same supplier.
Right. Ideally, every batch is slightly different. When it comes to compatibility testing, though, I would think one sample, one batch would be okay, because we're trying to get an overall feel, and we do realize that every batch does vary a little bit.
Okay. All right, and I do not see any other questions right now. Like I said before, if you have any questions, please feel free to let us know either here, or you can email Heather or Monica. Their information's up on the screen. All right, well, Heather, thank you for presenting that. That was great and very informative. And thank you, everyone, for joining us today. Have a great day.
Thank you. Bye.